Alright, we want to take a look one more time at electric field, potential difference, work, charge. Okay, just get a quick reminder out there. Now you guys are all aware that a positively charged particle creates a field around it, and a field is a region of space capable of exerting a force on another charged particle. Okay, so when we have a positive charge, we draw field lines away from the charge that look like this, right? These point in the direction a charge would go if we brought it up close, a positive charge. Okay, so if we bring another charge up here close, and I meant for that to be red, a red positive charge, okay, what we know is it's going to experience a force, okay, and that force is going to be away from this charge in the middle that's creating the field, and it's going to be proportional to the two charges between them. And that was Coulomb's law. Coulomb's law said the force between two charges is equal to Q1 Q2 over R squared times K, where K is the electric constant, and it's 9 times 10 to the ninth newtons meter squared per coulomb squared. Okay, so you have to remember when you're doing this equation that Q1 and Q2 both have to be measured in coulombs, and distance has to be measured in meters to get your units to work. Okay, and that gives us the force that this thing will feel. Well, that depends on both charges, and sometimes we don't want to know, we don't want it to be in terms of both charges. And so that led us to this idea of an electric field, okay, where we have E equals KQ over R squared. Now, what that tells us is when we have an electric charge, okay, and actually this one makes more sense in the uniform field, but this will work. Okay, when we have an electric charge and the field lines are going away from it, you know, because it's a positive charge, okay, what we can say is at any given point in this electric field, okay, we can tell how much force a charge will feel per unit of charge. Okay, so on this line, which was supposed to be equidistant from that charge, it doesn't matter what we put here. We're going to say the electric field at that point is equal to KQ over R squared, and so no matter what charge we put here, okay, it's going to feel a force, and that force that it feels is equal to E times, that's an E times Q, because what this tells us, and now we have to be careful. Okay, this electric field thing here, this is based on the central charge Q. Okay, but the force that a different charge particle out here feels, this Q, is actually based on the test charge. Okay, so you got to be careful when you're doing this. Strength of electric field depends on the charge creating the field. The force on the particle actually depends on the particle. Okay, so this thing is going to feel a force this way, and what we say is electric field strength is measured in newtons per coulomb. Okay, and so that tells us every unit of charge will feel this many units of force. Okay, so if I put a bigger or a more charged particle here, a particle with more charge on it, it'll feel a bigger force than a particle with less charge. Okay, that's all electric field is. It tells me how much force a particle is going to feel a given distance from the charge creating the field. Now, what we're really interested in, okay, besides Coulomb's law and electric field, is work done to move a charge. And so it's easier to think of this when we have a uniform electric field. And a uniform electric field is interesting because when you have a point charge, distance matters. When you have a uniform electric field, it really doesn't. Okay, and so what we get is we have two plates, okay, that are separated by some distance, and one's positive and one's negative, and of course that's going to set up for us this field that moves away from positive and towards the negative side. Okay, so we have this uniform field, and we draw those arrows that look like this. And what we think about in here is, well, what if there was a charge that we were trying to move, and we wanted to move it against this. So if this is a negative charge, it would be pulled towards positive, away from negative. How much work would it take to actually move this charge here? Well, remember, we have work equals force times distance, okay? And the force that this thing feels is equal to the electric, the force that thing feels is equal to the electric field times Q, okay? But basically, okay, we again want this to be independent of that charge. So if there were two charges, a bigger one and a smaller one, and we wanted to know how much work it takes to move them, well, we'd have to do electric field times distance, but it would be different because E equals F over Q, right? So this is the force on the particle divided by the particle. And so we put these two things together and we basically come up with the idea that the work done to move a charge a distance through this, okay, is force times distance, which is E times Q, okay, times D. This tells me how much work is done on each one of these particles. And so this Q comes into effect. If we actually just talk about the work done to move any particle through that field, then what we're talking about is work divided by charge, and work divided by charge is just back to E times D, okay? The distance that we move it times the electric field. Now this is what we call potential difference, okay? Potential difference is how much work it takes to move a charge from one place in a field to another place in a field, but it's per unit charge, okay? So electric potential difference is the change in potential energy, right? Because work is energy, work is the transfer of energy. So electric potential difference is the change in potential energy per unit charge in an electric field, okay? So I'm not saying it takes the same amount of work to move this charge from here to here as it does to move this charge from here to here, okay? Since this charge is bigger, there's more charge, it takes more work. However, per unit charge, it takes the same amount of work because they're in an electric field, and that's what potential difference measures. It says, okay, we're going to take the amount of work divided by the charge, the amount of work divided by the charge, and that'll tell us the potential difference between these two locations in our field, okay? And so electric potential difference, delta V, is work on charge divided by charge. The other way you can think about it, okay, is so you have work on work on charge divided by charge, or electric field times the distance, and this is equal to the change in energy per unit charge, or what we call potential difference, okay? And this is measured in volts. So don't confuse delta V potential difference with its units volts, okay? A volt is the unit of electric potential difference, and it's equal to a joule per coulomb, okay? Now, one more little topic today, and then we will move on to current electricity, okay? Actually, that might be our next little topic today. Let's see. We know that if we put an electric charge in a field, it's going to move. Okay, it's going to go from here to here, and when it does that, it's given up all its potential energy, right? It's moved from this side of the plate to that side of the plate. It got to where it wanted to go, and so now it's done doing anything. Well, what if we had an electron pump? Okay, so we put something over here that pulled charge off of this plate and moved it into that plate. Okay, so we maintained a potential difference here. So even though we kept adding, even though charge kept going this way, okay, if we had something over here that could then pull that charge off and force it back down, okay, then we would get this continuous flow of electrons, okay, or charged particles, whatever they are. And this is actually what we get when we build a circuit. Okay, and an electron pump is not that hard to come by. You guys know them already. These are usually batteries, but when you plug something into an outlet or whatever, okay, when you're providing that electric energy, you are actually providing a means to maintain a potential difference between two places so that charge can flow. Okay, and that'll be our next topic. Okay, there's a little quiz today over Coulomb's law, electrostatics, just to finish up that unit, and then we will get started on current.